Hi, this is Dr. Hasan Abdullah with the course Introduction to Natural Language Processing. And we are at the ninth topic as per the course outline. So the lecture is 9. The topic is language model and the subtopic is large language models. So therefore it's C, 9C. So this lecture uses the supplemental material available at easymcq.com/goget. And that supplemental material is basically a learning management system. To be more precise, it's a personalized learning management system. How it's personalized? Because your route through the learning is not fixed. You can personalize it based upon the level of learning. How you do that? There's a video number 1. You may like to look at it and take benefit out of it. You can also go through a personalized route by performing searches, by preserving the order of keywords or with a free order of keywords. How you do that? That's shown in video number 3. You can also personalize by having a user interface as per your liking or even as per your needs. So that's how you do that. Please look at video number 4. You can also have a personalized evaluation, okay, through personalized online exams. So you get online testing, online grading, and analysis of overall results of how many exams you have taken of which subject and so on. How you do that? That's shown in video number 5. And of course, animations are also there. So where are those videos and where is the video of the remaining topics of this course and for other courses? So all those videos are available on my YouTube channel and on Canvas also. So if you go to YouTube and type my name, Dr. Hasan Abdullah, you will get access to all of these videos. So this is the course topic list. So right now we are at the language model. Okay, so let's move on to the supplemental website. So we are at the supplemental website. So the first 5 concepts in the form of questions with detailed answers were covered in video number 9A. And then of course the techniques of GPT and hidden Markov model for language modeling was covered in the lecture 9B. So now we move on to the large language models, the concepts which are presented in the form of questions and very detailed answers with diagrams. So what is large in large language model? Okay, so let me explain it using numbers, quantifiable numbers. So first is the number of parameters. The number of parameters are very large. I will quantify it as compared to standard or traditional language models. The data which gets trained or which gets, I'm sorry, the data which is used for training, that is very large. I'll give you the exact numbers also. Then the context length, how far you are looking, and of course to use all of this you need extensive computational resources. So of course they are extensive resources. And then we look at the model performance also. There are other things also. For example, the number of states which I have not mentioned here. So I'll touch upon it because this is a detailed thing. So a language model is termed to be large due to the massive number of parameters. Number 1, number of parameters, extensive training data. So this is basically we call it the dimensions. So the language model has large number of columns and large number of rows also. So parameters are the columns and high computational requirements. So to process all of this, you need extensive computational power also. For example, GPT-3 has 175 billion parameters, right? And trained on 517 gigabytes of textual data, which is a huge number. And for this, you need to have very powerful machines, right? So that enables is to provide impressive performance. Where in such applications, translation, question answering, and so on. The number of parameters, for example, it has 175 billion parameters, while smaller models might only have a few million parameters. So the richness of a large language model is way ahead, scales of factors more than a traditional language model. So what is the benefit of having all those large number of parameters? So that captures more intricate patterns in the language, okay, and it results in improving the performance of the output produced so that it is more human like. Because it is not limited to a certain type of task, but it is human like for translation, for question answering, for summarization, and the list goes on. Then let's look at the training data. So it is estimated that GPT-3 was trained on 570 gigabytes of text data. So we already know that text data takes very less space as compared to other types of data, so it's humongous. And where that data came from? That data came from books, that data came from websites and articles. The corpus is very diverse, okay. So what is the benefit? The benefit is that it allows to capture the topic and nuances, okay, across diverse domains, generalized text, okay, and of course that can be have different domains are used. Okay, let's go ahead. So the context length. So this is much more than that. GPT can process and maintain context over, for instance, 2048 tokens of text in a single pass. Okay, so this allows to generate more coherent responses, unlike unigram, bigram, trigram, or whatever, right? So, for example, if we have a vocabulary of 10, so if you add up all of them as unigram and bigram and trigrams and 4 grams and 5 grams, they end up like being 1,000. They end up being 1,000. Okay. So when we look at the context length for large language model with the vocabulary of 10 and using web embedding, you can imagine how many what's the strength and the depth. So what I was talking about, that was with reference to the number of states, which is not discussed in detail over here. Okay. So what is the computational resources? The computational resources required, uh, it involves thousands of GPUs, and they crunch the text over several weeks. I will give you the references. It's not something which I am coming up with. Okay. And of course they cost millions of dollars, right? So it requires massive infrastructure, it requires people resources, it requires large energy generation and consumption requirements to handle these size of models. All right, so about the model performance. So these models perform better, not they are limited, but they're better for example question answering, for translation, which I've already mentioned, and summarization. The list goes on. And then there is something which is called as a few shot and zero shot learning, okay, which I will discuss in this lecture, and I'll show you a diagram also. So now you know why large is used in large language models. So as my promise, here are the references. So there can be more also. So please, if you're interested, you can go through them. So how do these large language models differ from traditional language models in terms of the results produced? Okay. First of all, as I mentioned here, that they can look at 2,000 tokens in a single pass. In a single pass. So they can look back a lot. So handling long range dependencies, right? So and they also have the contextual understanding that these words are used in which context and what would be their meaning, and based upon which they predict the next sequence of words, right? So I can give you a long list of words which have different meanings, but they have the same spelling and the same sound also. For example, bank. For example, bark. For example, river. Spelling is same, pronunciation is same, meaning is altogether different. For example, bat, and so on. For example, male. So contextual understanding is very important. Okay, and it cannot be based upon looking back 2 words, words, and so on. Okay. Training data set scale, the scale of data which is used to train the large language models that reflect extensively on the results produced. And there is a few shot and zero shot learning. Zero shot learning is almost, so they are trained so much effectively that they can be presented with a statement, which I'll do in the example, a mathematical statement, and without having prior training they come up with the correct answer. That's zero shot learning. And few shot is that look at few of those prior statements or parts of the corpus. And the task flexibility, they are not limited to one or two tasks. Okay. And they are also not limited to one or two domains also, which we will cover in transfer learning, okay, in this lecture. So what are the details? These are the details. So so the accuracy and the diversity comes from the large volume data which is used for training, and not because it is trained in contextual training. That's very important. So the difference in the why the difference in the results produced, okay, is because of the models like ngram, which struggle with long range dependencies. Okay, because of the limited context window. As a matter of fact, as we discussed before, that context window may not be fixed. That is could be dynamic. Okay, so when the window size is fixed, it creates problems. and does not allow these techniques, right, to maintain context over long passages. But using self-attention, large language models maintain context over long passages. Okay, therefore they can be better at handling the relationships between distant words. And what it results in? It results in better results produced. Okay. So next, let's look at the contextual understanding. For example, like simple models depend upon last few words to predict the next token. Okay, and the context is limited. But these large language models, they capture, because of the way they have been developed, the way they have been trained. They have a broader context and meaning. Okay, across larger sections of the text. Okay, so what's the result? The result is coherent and contextually accurate outputs as compared to traditional models. So the quality of the results is much better of the large language models as compared to the traditional models. Training data scale, that we've already mentioned, I've already covered actually. So few shot and zero shot learning, this I will cover. I have a full question and a concept. So they can perform tasks with little to no additional training. Large language models capable of performing additional tasks at little or no additional training. Okay, because they can generalize to new tasks by leveraging patterns. Which patterns? Which they have learned, where they have learned it from the massive amounts of data, which is lacking in traditional models. Then is the flexibility of the task. They traditional model requires task specific training. For example, this model is trained for translation, this is for summarization, this is for question answering, and so on. Okay, but the large language, so, and of course when the training is not there, and the traditional model trained on translation is used for summarization, is not going to provide the desirable results. But that is not the case for the language models, large language models, I'm sorry. So what does this picture means? I think it pictures clears the concept that what is a large language model and what is not. If you want to know more about it, here are the references. All right. So let's move on to step-by-step working of large language models. So these are the steps. So basically, what's happening? Actually, within these steps, there are multiple steps. As you can see, the reading time is 2 minutes 30 seconds, 2.5 minutes. A lot of text here to be read and understood. So one is the pre-training. So before the actual training takes place, okay, pre-training takes place, and to a certain extent, and this is without any human supervision. So you can say the embryo or the embryonic kind of a model is created, and then the fine tuning takes place under the supervision of humans, and then is the prompt based learning. So what are all of these things? I will go through all of this. So before actually I do that, what I'll do first of all, so let me first show you the working in a diagram, and then I will go into the details. Okay, so we start with the first step. Okay, so in this step what we do is that we have the unlabeled data and we have the proprietary data. Okay, and based upon this, okay, there's something which is called as self-supervised learning takes place. So first of all, in self-supervised learning, there is no pre-training, there is no human involvement. So what happens in self-supervised learning is that that text is used for the training purpose, and the parts of the text are generated. All right, and those generated ones, they are compared with the actual one, and that's the way self-supervised learning takes place, right? So what this results into something which is called as a base model, which I also quoted as an embryo. So basically, it's an embryo of the final model. Okay, so once it has been trained, then it is trained using narrow data sets. It means domain specific data sets. It gets trained, that base model, and whatever is the resulting model, that is evaluated by humans, and humans not doing any major work. Human involvement is in fine tuning. That's step number 2. And when this base model has been fine tuned based upon the human feedback, okay, then we go to step 3. And in this step 3, there is human prompting. Okay, with, of course, they are domain experts, and then there are direct and indirect prompts which are non-human. Okay, And what we are doing is that we are fine tuning this base model, and based upon the prompt based learning, right? So prompt is made and the result is delivered, and based upon that result, that model is fine tuned, and ultimately we have the prompt based learning and we have the augmented model. So this is what happens. Of course, that requires a lot of resources, processing power, energy, and so on. All right, so let's the step one. So the step one consists of data collection. So what the in the diagram, it's not possible to draw everything which is mentioned here. Okay, so that diagram was kind of a summary to give you an abstract understanding. So you need to have data collection, and that data is unlabeled. And the corpus consists of books, websites, articles, proprietary data sets, and so on. So we have a huge corpus, okay, from diverse sources. Okay, self-supervised learning. The model learns patterns and structure in data without human annotations. So how does it happen? Learns to predict missing words in a sentence, right? And of course, those words could be removed intentionally, and then based upon the results, the model learns. Okay, and of course, in a sentence or next word in a sequence, right? So that's self-supervised learning. Then is the representation learning. The model learns features like grammars, facts, reasoning, and contextual relationship between words. How it learns? Because it basically generates those words, right? Which could be which like as we do in part of speech tagging. And if they are not grammatically correct, they are corrected, and so that's the learning takes place. Okay, it generates embeddings, numerical representation of the text, which we already covered. I think it was maybe topic number 4. Training objective. Okay, what is the objective? Objective is to predict the next word. That's what the objective is, given the previous tokens. Okay, so it could be masked language modeling. Now I'm not going to a lot of details because this course is an introduction to natural language processing. This course is not about large language models, or we can have auto regressive modeling for GPT. And in this step number 1, there's no human intervention, there's no human supervision. Okay, so it is all unsupervised or it is self-supervised. Okay, so once the step 1 is over, then we move on to step number 2. What is step number 2? This is the step number 2. So what happens in step number 2? Okay, in this step we have a pre-trained model. Okay, so where does that pre-trained model comes from? That comes from step number 1. Okay, so that is the pre-trained model. So now it is adapted, right? That was more generic to specific data sets for some specific annotations. Okay, for example, sentiment classification, question answering, and so on. So what is the purpose? Fine tuning. Okay, so we have a supervised. So for supervised fine tuning with these narrow data sets, the model starts to learn from human labeled data, and the labels provide explicit guidance. Okay, in how correct answers or sentiment labels, right? Because remember that sentiment analysis is not limited to only happy or unhappy or sad. There is a whole spectrum of sentiments which is covered in probably towards the end of this course. So the model is fine tuned how based on the human feedback, and who gives that feedback? Domain experts, or it could be users also, and that refines to reflect the real world use cases. And what it does, it like it improves the quality of the predictions. That's what it does. All right. And of course, after this human fine tuning, the understanding of the model improves. Okay, and it can handle specialized applications. Okay, and from the help of domain experts. What is the specialized applications? Like customer support, like in healthcare, like in legal analysis, like in uh, travel and tourism, like in arts and literature, like in finance, and this goes on. So then we move on to the last and the third step. So what happens here that the model is used with various prompts. Prompts are the questions, both direct and indirect. Okay, which guides it towards specific behaviors or solutions. So there may be direct prompts which are more specific. Okay, and there are indirect prompts which involve setting up a scenario. Okay, and then humans directly interact with the model using prompt engineering, which is a domain in itself. Okay, and they construct by hand and they adjust by hand the prompt. And what is the purpose? To refine the model's behavior. And we may be, and of course, it adds value. So we are here with prompt-based learning. So the model iteratively improves its responses. One iteration better, second iteration much better. How? Through user interaction. And then it is fine-tuned for specific goals and targeted targeted tasks and so on. So this is the explanation of this diagram. So I mentioned earlier something called as transfer learning. So what is transfer learning? In a nutshell, transfer learning is that I have a large language model, of course trained on large data set for certain tasks, certain domain, right? And transfer learning means that I can use that model after training on a smaller data set for some other domain, because there might be commonalities between those two domains, and the domain for which I'm using, okay, for which it was not trained, they may not have sufficient data, right? So that's transfer learning, and it actually happens also. So what is transfer learning? Utilizing a pre-trained model on large amounts of generic data. Generic data is available in large volume, of course, and then I fine tune it for specific task using task specific data. Not only the data is task specific, it is in small amount also. So the knowledge is transferred from the general domain, right, to a specific or specialized domain. So this helps the models to generalize well and reducing the need for large labeled data sets. They may not be available altogether for the specialized domain. It's a very interesting thing. And of course, that saves on the computational resources, computation time, and people resources, and memory resources, and energy resources. So there is pre-training. Okay, model is trained on a large data set, on a generic large data set. Okay, and what it does, it learns the general language patterns, grammars, contextual information of that language, and that what is that the model learns, that is applicable to any domain for that language. Okay, so what happens, that it becomes very proficient in understanding diverse linguistic structures without specific task related data, which comes later. So one is the pre-training, as we did in the previous conceptual question. That was step one. And there is the fine-tuning phase, as we did before also. The model undergoes fine-tuning with task-specific labeled data. For example, healthcare, for example, law and compliance, for example, travel and say tourism, and so on. So the fine-tuning adapts the model, which was trained on a large generic data set, the nuances of the target domain. Step two of the previous case. And is the task adaptation. So the model trained on one task to be adapted for another task. Okay, with minimal additional training. Okay, and then it excels in different domains also. So knowledge transfer takes place. Where is that knowledge? That knowledge is stored in the model itself. So if it's GPT, it's stored, the knowledge is stored in the neural net, right? The weights of the connectivity and so on. And knowledge transfer learning leverages the knowledge gained during pre-training, transferring into downstream. For example, it could be healthcare. So LLMs benefit from large-scale training on diverse data sets, even when the target task has limited data, because the language is the same. Model can adapt to new tasks with fewer resources, fewer time, fewer less energy. So this what does it results? It results into domain specific, okay, models trained for domains using domain specific data. So something which was trained on general language data can be fine tuned for medical, legal, and so on. So if we look at this diagram, so what we see is that this is the large amount of data and labels. These are the labels. This is the data. This is the model. So the labels and the data, which is generic textual data, that goes into this to the development of the source model, and the transfer learned knowledge, that goes to the target model, which has limited target data, which has limited target labels for the healthcare domain. And the transfer learning basically enriches, okay, and you have this target model without having sufficient target labels and target data itself. Wonderful approach. Okay, so what is a few shot and zero shot learning in large learning models? Okay, and I'll give you examples for real life mathematics. So already this lecture has taken too much time, so I will be kind of short here. So we have this one shot in few shot learning. The model is trained with just a few examples. Okay. So if Mary has 3 apples and buys 2 more, how many apples does she have? So after looking couple of such examples, the model is able to generalize. Okay. And of course, there could be different numbers, there could be different scenarios, different people, different objects, different items, and so on. And zero shot learning, okay, a linear equation such as 2x plus 3 is equal to 7, right? So given only a description, solve for x, the model solves that what should be the power of x. So when x is 2, you have the 7. When x is 5, okay, or x is 3, then you have 13, right? So this we achieve after a lot of extensive training of large language models. So over here you can see that we have a few short. So based upon these two scenarios, one scenario basically, and then there's a question and you get the correct answer. And zero shot, there is no scenario, just a question, and then it will get the answer. And of course, let's think step by step. This is not generated by the machine. That is correspondingly there. Okay, most probably human inserted. Okay, so if you are interested in learning, then you should be. So these are some references. So that's all for this topic. Thank you very much.